Hey everyone, today I'll be explaining my solutions to leetcode-biweekly-contest 310, and the difficulty of this contest is fairly easy. The first three problems were fairly easy and the last one is a bit interesting. And let's start with the first problem. So the first problem is we are given an integer array nums and we need to return the most frequent even element. And if there is a tie, return the smallest one. If there is no such element, return minus 1. Right. So in order to solve this problem, we can use a hash map, and in order to ensure this smallest one, like this constraint, we can use a map, C++ map, and it will take care of this case. And if there are no such elements, like if we don't find any even element, we can return minus 1. So this is just a simulation of what they asked. So I'll directly show you. So create a frequency array, and first create another variable to keep track of the maximum frequency, and if it's an even element, add it to the hash map and then add it to the map, and then keep on updating the maximum variable, maximum frequency, and then at the end check for each value whether its frequency is same as the maximum frequency. If that's the case, return the value. So this will make sure that you always return the smallest value in case of ties, and in other cases just return minus 1 if you don't find an even value, right? So the second problem is optimal partition of a string. So here we are given a string as partition the string into one or more substrings such that the characters in each substrings are unique. That is, no letter appears in a single substring more than once. Okay, and you need to return the minimum number of substrings in such a partition. Okay, and also that note that each character should belong to exactly one substring. So yeah, so that means you need to partition the string. You need to partition the string at different indices, such that each partition will only have unique characters, and we need to return the minimum number of such substrings in the partition, right? So this is in order to ensure this thing, we can always this thing will always be ensured if we maintain this condition that the characters in each substring are always unique, right? So for that we can maintain a set data structure, and when we traverse the input string, we can always push characters in the set data structure, and whenever we meet a new character which is already in the set, we know that we cannot continue the current substring. So we start a new substring, that is, we make a partition over there, and then we start a new substring, and we increment the answer by 1, and so on, right? And we do that for all the characters. If the new character we see is not present in the set we are maintaining, that is the current window or current substring, or whatever you want to call it, we can continue the current substring, we can extend it and move on to the next character. But in that case, if the character is already in the set, you start a new substring here, so that is, we are making a partition at this position. And yeah, so initially we can say that answer will always be at least 1. So for that purposes, we can initialize the answer as 1 and then start this process. So this is also just a simulation of what they have asked, nothing special here. And yeah, so for that I'm initializing the answer as 1, and because we already know that at least the answer should be 1, right? And yeah, this set is just a current window, it just keeps tracks of the current substring, and we have two cases for each character. If the character is already present in the set, the character is already not present in the set, insert the character in the set, and then if the character is not present in the set, start a new window and increment the answer and return the answer. That's it. So this will, like, there is no minimum number of substrings in, like, this condition. It is like a redundant condition, because if you ensure that each substring contains only unique characters, you will always like there is a possibility, like, for example, we may the purpose of the reason for giving this condition could have been to, uh, for example, in this case, we are partitioning AB together. We are partitioning AB together, right? So we they don't want us to partition A separately, B separately, and then A separately, and so on. So in that case, the answer will always be n. There will be n partitions always, right? Because each a single character is always unique, and we can break n length string into n characters. So in order to take care of that case, they are giving this condition. But yeah, so in this way we can always solve it. So let's go to the next problem. So in this problem, we have an intervals array, and both so each interval represents range and both inclusive, and we have to divide the intervals into one or more groups such that each interval is in exactly one group, and no two interval that are in the same group intersect each other, right? And we need to again return the minimum number of groups we need to make, and this is two intervals intersect if there is at least one common number between them. So this is trivial. You can check if two intervals is intersecting or not by using the left and right values, comparing the left and right values of each intervals. But what we are interested in this problem is how we can find the number of required groups, right? So this is a very standard problem. There are a lot of similar problems in LeetCode, like meeting rooms and similar problems. This is one of such one of its variation, I guess. Here we can say that the minimum number of groups we need to make is the maximum the value which is occurring in most number of intervals, right? The particular point, like if you plot all the intervals in a straight line, and you put straight lines like over each values, like 1 2 3 4 5 6 for all the values, and you see and you count the value which is occurring, which cuts most number of intervals, right? That value will be the answer. So that is because we always need to make sure that no intervals intersect together, right? So it will be like this. For example, this is the number line. We have initially a range, let's say 1 and some range n, and we have few values here, and there are certain intervals, right? So these are the intervals given to us, and we need to find the minimum number of groups we can make, right? So what I was saying is, if you just draw straight lines at each point, and then you count the total number of like intersections at each interval, right? So for example, for this line, it intersects at 2 points, right? Similarly, this line intersects with 1 2 3 points. This line intersects at 1. Okay, so this is also here, 1 2 3. Again this line 1 2 1 2 2 1 1 2 1 2 1, right? So we can say one thing, that we can never group these three values together, like these three intervals can never group them together, right? So we at least need three groups in order to separate them differently, right? So this will sort of establish an upper bound to the answer, and then we can again see that it's not always it's not greater than or equal to the upper bound, and it's actually equal to the upper bound only. The way we can say that is that we know that this is the maximum number of intersections possible in each group. If we can make that number of groups, there won't be any new intervals that will be intersecting with this interval, which is in the same group of this interval, right? If that is the case, that interval would have been in our answer. Like that interval would have the maximum frequency. So in that way, we can say that the answer is always equal to upper bound. So, so in order to find this maximum frequency, we can use a difference array, and we can uh, so so this number line in order to represent this number line, we can use an array, and that array will be the difference array. And and the way in which we create these ranges is using the difference array technique only. That is, whenever we have an interval of interval L comma R, we do difference of L plus plus and difference of R plus 1 minus minus. That is, so this particular thing uh, represents that we want to increment all the values in the range L comma R by 1. So we do this once for all the intervals, and then we take the prefix sum of this difference array to get the actual value at each nodes, right? At each indices. So that will give us the total number of intersections, and that is our answer. So let me show my code. Yeah, so we create a difference array of size 10 power 6 plus 1, because the range of values intervals we can have is up to 10 power 6. And then same logic applies here. We create L and R, and then difference of L plus plus, and if R plus 1 is lesser than max, this is just to avoid any segmentation error. And yeah, difference of R plus 1 minus minus, and then you take the prefix sum of all the values in the difference array and return the maximum value in the difference array. So that will be the maximum frequency. That is the maximum number of intersections, right? Okay, cool. And so one more thing here to say is that this particular approach works perfectly just because of this range 10 power 6. If the range is like very high, there is an alternate approach. Instead of using an array, we can use a map, and we can do the same thing, but instead of using an array, we can use a map, and the same logic will work. So in that case, ranges won't be any issues, right? So the last problem is the interesting problem in this contest. So the problem says that we are given an integer array and an integer k, and we need to find the longest subsequence of nums that meets the following requirements. The first requirement is the subsequence should be strictly increasing, and the difference between adjacent values, the subsequence is at most k. Okay, and we need to return the longest length of the longest subsequence that meets the requirements. So, so and we already know what a subsequence is, and so this particular problem is a variation of longest increasing subsequence, where the adjacent elements just differ by k, at most k. So how do we solve this? So this problem requires one key observation. It's not an observation, but if everyone, like before saw, we know that there is an order of n log n solution to LIS problem, right, using binary search. But there is a order of n square solution to LIS as well using DP. That solution is we'll use that solution to solve this problem actually here. So in this particular order of n square DP solution, the DP states are DP of AI is equal to, for each AI, this is the DP state, DP of AI is equal to 1 plus maximum of DP of AJ for all AJ lesser than AI. So this is a DP state, and in order to find this maximum of DP of AJ for all AJ less than AI, we'll use one more loop, hence the n square time complexity. But in this case, our constraints a bit different, right? So let's rewrite this dp state for this particular problem. So for this particular problem, dp of ai is equal to 1 plus maximum of dp of aj. Again, everything remains the same except for all aj such that absolute difference between we can say like this, yeah, such that ai minus aj is lesser than or equal to k. So this gives us some hints, right? So this tells us from where to where the aj, what is the range of aj, right? This particular expression tells us what will be the range of aj. If we have a value of let's say ai equals 5 and k equals 3, we know from where to where aj can lie, right? So that is obviously from so the end point is 4 and the starting point is 5 minus 3 2. So aj can take values anywhere in this range, so aj belongs to this particular interval, right? And we just need to make a max query in this range and ask all the dp of aj values, and then just add 1 to it and update the dp of ai to it, right? And if we do this like naively, it will take again order of m square time. So how to optimize this maximum of dp query, right? So that is again trivial. We can use a data structure like segment tree, which will help us, which will give us the range maximum queries. And the reason why we are using segment trees here and not any other data structures here is we need to make point updates as well, right? As soon as we find the dp of ai value, we need to update that value in the segment tree, so that when we move to some other ai value, we can query uh, when we move to some other ai value and we query for the dp of ajs in the new ai, this particular ai, the previous ai could be a candidate which satisfies this constraint, right? In order to always keep all dp of i's updated, we should every time we make a dp, we make a every time we see a new value, we need to update the dp value in the segment tree, right? So instead of creating a dp array, we'll create a dp segment tree. So that is the single logic here. The same way we solve the order of n square or dp solution for lis problem, we will use the same logic, and just instead of using a dp array, we'll be using a dp segment tree. That is the only difference in this problem and nothing else. And the range in which we'll make the range maximum queries is just so the range is just ai minus k to maximum of 0 comma sorry, the range in which we'll make max queries is just maximum of 0 comma a minus k comma ai minus 1. That's it. So for each ai, we'll make a range max query in this range and add 1 to it and update the dp of ai value. That's it. So this is my segment tree code, segment tree template, and here we'll so yeah, I'll create a segment tree of length 10 power 5 because so this particular approach also works because we are already given that the range of values cannot be greater than 10 power 5, right? So this is a key hint here. So using this fact, we can create an array of size 10 power 5 and pass it to pass it to segment tree. I'm calling this segment tree as dp because that is what it is here, and it will answer maximum queries. And initially the answer, like, so we can say that at least the answer can be 1, right, in all the cases, because the length of the array can be at least 1 and we need to find the longest increasing subsequence. So each element is a increasing subsequence of itself, so by itself. So hence we'll say answer is equal to 1, and then for each AI, as I said, the range L is equal to maximum of 0 comma AI minus k and R is AI minus 1, and this is just to ensure that we are not making any segmented any runtime errors or something. And so this is the maximum value that range maximum query will make. So we'll do the range query from L to R in the segment tree, and as soon as we do the range query, we'll update the new DP value at this position AI as 1 plus max, and where max is the range query which we did. And so this is equivalent to writing DP of AI is equal to 1 plus max, but since this is not an array, this is a segment tree, so we have to make the updates like this one. And then of course we need to update the answer, that is the longest increasing subsequence ending at AI. So yeah, I forgot to say, I forgot to tell the state definition here. So in order of n square solution, dp of I represents the length of the longest increasing subsequence ending at I. That's it. The same. The everything is same here from the order of n square solution of n LIS. The only difference is instead of using your DP array, we'll be using a DP segment. That's it. Yeah, and then we'll return the answer. Yeah. Thank you.